Okay, so welcome everyone to this lecture. We're very lucky to have Dr. Wendy Siman here today. So we went to graduate school together. We overlapped a little bit. He was a bit ahead of me, but Simon was a master's student in medical physics at Columbia University in New York. Then he did his PhD at MD Anderson Cancer Center in Texas, where he worked with yttrium 90 radionuclide dosimetry. He then went on to become an assistant professor at the University of Tennessee, followed by the last 5 or 6 years, he's been at the University of Colorado Anschutz School of Medicine. And yeah, he's has over a decade experience in nuclear medicine, so he's well experienced in this domain that he'll be talking about, and he'll be discussing sort of the physics of nuclear medicine imaging, both on sort of the planar imaging side and on the tomographic imaging side with PET imaging. So take it away, Simon.
Yeah. Thanks, Joe, for the introduction, and thank you everyone for coming. I know that it's late for you all. Hopefully, I can show you guys like a thing or two, and then you learn something. So, in this, what I'm showing you right now, hold on, let me see, where's my cursor? Okay, so what I'm showing to you right now is like there's two things. So, like the image quality on the left side,
Simon, share
and
your slides.
oh, I haven't shared it. Hold
Yep.
on, where's my? Hold on. Okay, can you
There
see
we
it
go.
now? Again, a couple things that I'm showing you right now. So on the left is a phantom image. It shows the image quality. So let's just start with the resolution. So like as the two left here are CT images. So this is a phantom, and these are resolution, and this is the uniformity regions, right? And this is CT images. And the right hand side, these are the PET images. So right off the gate, you can see that resolutions is worse in PET versus in CT, right? And then when you're looking at the uniformity, look at how uniform the CT image is versus you see blotch and patches here in PET, right? And then on the right hand side here, you see some imaging procedures like from CT, from X-ray, and from nuclear medicine. So the second and third columns here are the dose. So if you're familiar with CFERT, you can use this column, or if you prefer to compare it to the background radiations, you can as well. So if you compare the patient dose, like here we are for nuclear medicine, so it's like 25 or like 8 years, just say for discussion's sake, versus if you look at like other modalities, it's not even it's not even close to nuclear medicine, right? So it begs the questions like, why are we interested in something that have like poorer image quality, resolutions worse, uniformity worse, and then the dose is higher? So like, why are we interested in this type of modality? So on the three group on the left, obviously this is a brain imaging, right? You can see like CT images, MR images, and this is FDG PET images. So if you're looking at just this MR and the CT, can you tell if this is a patient, a live patient, or this is a cadaver? You cannot, because like both MR and CT are anatomical. So it gives you like just the anatomy, you cannot tell whether the brain is still alive or it's dead already. Versus if you look at the FDG PET, right? So FDG, the fluorine 18 is a glucose analog. So like the brain still metabolize the sugar, or the sugar analog in this case, right? And it shows you brain activity. So you can tell that the patient is still alive. So on the right hand side here, you can see this is a brain death patients. So there's no activity in the brain at all. So this is why we're interested in nuclear medicine imaging, because this is a functional imaging versus the anatomical. And these are some other nuclear medicine study. You have a bone seeking agent. So, like it seeks for the bone, and then it looks at the tumor. And then you have like, fecal scan. This is like, ventilation and perfusion of lung. And then you have cardiac perfusion and gastric emptying. So these are all like, functional imaging that you cannot do with just like a X-ray, whether it's CT or like, even like a MR probably like have some functional, but it's different mechanism. So the talk for today, I'm going to discuss, it's a very basic nuclear medicine imaging introduction to it. Initially, Dr. Wagan actually asked me to present PET, but I think like, for the introduction, it's good to present it in like, nuclear medicine, planar, spec, PET, and I will compare it with X-ray or transmission imaging that you are all more familiar with. So the agenda for today, so like I'm going to discuss three imaging modality, and it's heavy on the planar side because like it's like when you first learn about transmission imaging, you spend a lot of time in the X-ray, right, the general radiography, and then I will discuss about the image formations and how they are different from transmission imaging, and then I'll discuss some performance characteristic of those modalities. So first, let's discuss like, okay, so like how do we achieve functional imaging? The answer is drug actually, like so these are drugs that like that's metabolized by the body, right? So you have, let's say, like you have your target. In this case, these are a cancer cell, and you have a drug that's actively looking for the target protein, right? And then you link the drug with a radionuclides. So the radionuclides, in this case, for imaging, you can do like a diagnostic agent, or you can link a therapeutic agent. So that's the field of theranostic, whereby exactly the same drug, you can do like both therapy and imaging. So what do I mean by radionuclides? So, like the graph that you see here is the graph of the number of proton versus the number of neutron on the y-axis here. And the black curve here is the equal number of proton and neutron. And as you can tell that, the blue line here is the line of stability, means that, the radionuclides are stable on that. And as the element get heavier, it prefers higher number of neutron. The reasons being is that it's an electrostatic versus nuclear force, right? The electrostatic between protons trying to repel each other, and then the nuclear force between the nucleons actually like what's keeping them together. So you have the line of stability. Anything like outside the line of stability is called it's called unstable. So they are radioactive. They will have to decay and go back to the line of stability. So like if you're on the downside, then you want to go up. If you're on the left side, you want to get in. And the decay mode, like there's like a few decay modes, but like what we're interested in is like this guy. So these are the gamma ray. So the gamma ray is our signal for nuclear medicine imaging. And then these are also of interest. This is a positron. We're going to discuss it in more detail, but this is your signal for PET. And regarding the decay mode and the radionuclides, I think like you can ask Joe. Like there's like lectures given by Ben, like it's very good lectures, and he discussed this in more detail. So I'm not going to repeat it here. And in terms of the radionuclides production, we in medical field, we don't really use anything that's naturally occurring because like it's not like the activity is not high enough. So like we have to produce it. So in the nutshell, how do we produce like radionuclides? So you start with something that's stable, right? And then you have to move it either to the left or to the right. So you bombard it with particles, right? Neutron, alpha, or proton. So like once they become unstable, then they will have to go back to the line of stability, and then they will follow these decay modes. So these are a table of radionuclides that used in nuclear medicine clinics. And I want to highlight a few things. So, like these are your positron. We're going to discuss it again, like, later in the second half, 30 minutes. So these are the PET, and the gamma are the nuclear medicines, right? And as you can tell, like this is not generally true, but, like on most cases, PET tends to be an organic element. So, like you have carbon, nitrogen, oxygen, and fluorine. So, like these are easier to make the drug compound because, like they're organic, right? And then the second thing that I want to highlight is the half-life. So for all the gamma emitters, if you look at the half-life, it's hours actually. So it's a longer half-life, right? Whereas for the PET, you're looking at it like, FDG, this is the workhorse of the PET, is 2 hours, but the rest is very short life. So these pose a logistical challenge actually, because, like when it decays so fast, right? Like, when you transport them, if it's produced like remotely, then, you have to start with a very high activity and it poses radiation risk, right? So, like the PET is harder in terms of logistic because of that. So, you have to have like the cyclotron or the productions method like nearby, like, and in some like a very exotic one, as you can see, like, it's within minutes, right? You have to have it on site, there's no other way. So let's discuss about our signal. So we have like a X-ray versus gamma, right? So what are the difference between X-ray and gamma? The answer is not the energy. Normally, when we look at like, okay, what's the difference between infrared, UV? It's the energy. And in this case, it is not the energy because if you can see, this is gamma and this is X-ray. They overlap actually. So so the difference between X-ray and gamma is the origin actually. So like these are your X-ray spectrum from like your X-ray tubes. So you have the Bremsstrahlung, the unfiltered Bremsstrahlung that is like this RAM, and then you have like the characteristic radiations or characteristic X-ray, or you can call it like fluorescence as well. So this comes from orbital electron. When they have like a vacancy in the orbital electron, then like the other shell electron from other shell will come down to a more stable state, and then it releases energy. And this is your X-ray. And in gamma ray, actually, we discussed, right? Like let's say like it emits a beta particle. So the daughter product is not always on the ground state. So like the daughter product can be on the excited state, and they have to come down to a stable state. And in doing so, they emit photons, and these are gamma rays. So the difference is that electrons originate from orbital shell, and a gamma ray originates from the nucleus from excited state to the ground state. And the similarity is that both are discrete in energy. So like as you have like because it depends on the level, right? The level of the energy. So in both characteristic X-ray and gamma ray, you can use it for spectroscopy because they are discrete. So now let's discuss like transmissions versus emission. So like I hope that like most of you are familiar with X-ray, and so those are transmissions, right? So you have your patients over here, and then your source is actually an external source. So you're shooting X-ray beam, and then what you're looking at is you're looking at kind of like quote unquote like the shadow of the patients. So the contrast mechanism is actually from photoelectric effect. And to remind you, like photoelectric effects, like one X-ray coming in and then it completely absorbed. So in this case, let's say like, we have like 100 photons coming in to the soft tissue and to the bone, right? Probably you will see, let's say like, you detect 40 photons in the soft tissue, and in bones, you only see 20. So that is like how you form the image, right? Like, in other words, in X-ray, your images are quote unquote like attenuation map. What you're looking at is the difference between the attenuated photons. Bone attenuate more than soft tissue. So, like the signal is lower in bone. So, like you will see probably something like this, so soft tissue and bone. So that's your contrast. In contrast with that, no pun intended, like, for emissions imaging, so this is your detector and this is your patients. Let's say like you have like two tumors with different uptake. Let's just say like, this is 5 times the background level. This is 10 times the oops, right on right. 10 times the background level, right? So what you see is that, you have like some counts here, and then you have like higher counts over there. So, your image is actually a radioactivity map. Where are the activities located? So it has nothing to do with the attenuations. So as the contrast mechanism arises from the uptake. So when you have like a tumor organ, what have you, that have like higher uptake of the drug, then you will have higher signal there. I think we discussed about that. Okay, so let's move on to planar image formation. So what I'm showing you here is a water phantom. The water is cold, so there's no activity in there. And let's say I put the spheres, like a small spheres, hot spheres, and I injected technetium 99M. So that is a gamma emitter, energy 140 keV. Okay, so we have like several photons that we can consider. So one is that photons unattenuated, so it hasn't interact with the phantom at all. Like it goes and go to the detector, and then so we can also have like the black one here. These are unattenuated as well, but it comes at an angle. So we cannot use this. The reasons being is that let's assume that we have this gamma camera, right? And then you detect the event here. You will have to assume that it comes from somewhere from orthogonal plane, right? Because you cannot assume that it's from the side. So these are your line of response. Okay. And the second thing is that you have a scatter that comes at an angle and a scatter that comes at an orthogonal, right? So the questions become, how do I isolate this, right? So what I want to isolate is unattenuated photons that's still at like 140 keV, and then I want the directions to be orthogonal to the gamma camera. So if you just image this without doing anything, you put a gamma camera here, and then you image this phantom, you will not see the spheres or the dot at the center. What you see is a curvature because of this, the primary that comes at an angle, right? So how do we solve that? So the first one we do is that we put a collimator. So the collimator, the function is to absorb the gamma ray that comes at an angle. It doesn't work 100% of the time. You cannot really stop photons, right? But it mitigate or it minimize the photons, the intensity of the photon that comes at an angle. So in this case, we've removed the gamma ray and this gamma ray that comes at an angle. So, and I want to highlight that the collimator, although it functions similarly with grid in X-ray, the purpose is different. So in transmission or in X-ray, you put a grid. The functions is to remove scatter so that it improves contrast. While the collimator in nuclear medicine does that as well, the most important function is so that for this primary that comes at an angle, right? Like I mentioned earlier, we have to make assumption that it comes orthogonal. It's from the line of response, right? So the primary functions of collimator in planar imaging or in nuclear medicine so that we can make this assumption. Otherwise, you will not be able to create the image. So in other words, the collimator function in nuclear medicine is to form the image. It helps you locate where the source is. And we discussed about these two, right? One is that this is the signal that we want. We detect it here. Okay, we can make assumption it comes from north. So you place the signal here. So now you see the spheres, right? And then when it comes from the side, okay, it's from the side. I want to make an assumption that it's orthogonal, but then it gets cut off by the collimator. So it's gone, right? So that's how you form the images. So the next question is that, okay, what do we do with scatter? This thing scatter, it lost its informations already. And then what do we do with this? How do we remove that? So again, some discussions about collimator. So this is just a septal. The septal thickness govern your energy, not energy, sorry, yeah, the energy of the gamma. If you're imaging higher gamma rays, you want this to be thicker, and there's the space here govern your sensitivity and resolution. It's always a trade-off. You allow more photons, your resolution suffer. You cut more photons, your resolutions improve, your sensitivity will suffer. And like I said earlier, the collimator is not perfect. You cannot stop like all the photons. So when you have a septal penetrations, and usually this is because the gamma ray has higher energy than the X-ray. So like in this case you have like septal penetrations, and it always look like a star actually. So you can see like it looks like a star here, and it looks like a star over there. And that's because, like if you look at your collimator, it's hexagonal in nature, right? So the answer to like, how do we remove this scatter, right? It's using the energy window as energy filter. So let's review it really quick. So the scatter in question is Compton scatter. So Compton scatter, you have a photons coming in, it interacts with the orbital electron, and then it goes at an angle, and then it ejects electron, right? So two things happen with the scatter photon. One is that it changed the direction, it lost its spatial informations, and two is that the energy is lower versus the original energy, right? Because it transfer energy to electron, so your photon's energy is lower. So that's how we can use the energy window. So these are the detected spectrum of the technetiums, right? The photopixels around at 140. So if we image the energy window here, and we design it as a primary, then you will cut off all the scatter down here, right? Because we just discussed that scatter have lower energy. So by doing that, you're removing these photons. But again, this is not perfect, because even in this primary energy window, you still have scatter, and we're going to discuss it really quick later on. Oh, I mentioned this earlier. So like in X-ray, your beam is polyenergetic. So like you have, if you look at the spectrum, it looks like that it is a continuous. And in gamma ray, or like in nuclear medicine, your photons is discrete. It has a discrete energy. However, when you detect it, it's no longer discrete. It has like some Gaussian-like spectrum, right? The reason is because your detector have finite energy resolution. It's not infinite, right? So to summarize, like we have like an event. So D here is the septal penetration. So your collimator doesn't work perfectly. A is what you want, unattenuated, and it comes at an orthogonal directions. And then B, this is scatter that happen in detector. So there's really nothing you can do. Like, if it deposits all its energy, then, like your event will likely be placed somewhere here. And if let's say like it deposits partial energy, and this one doesn't deposit its energy, then you will reject that. You will reject that based on the energy window, right? So like that event will fall somewhere here, and you just reject it. And C is like it's just a scatter that goes there. So now we've discussed the origin of the gamma ray and from the patients, right, and the collimator. Now let's discuss for the detector. So the detector that we use are scintillator. So what it means is that it is a similar technology with what you see in some of the X-ray actually. So scintillator means it converts the gamma ray to visible light. So one gamma ray coming in, you convert it to visible light. And so there's like some amplifications in there. And behind it is PMT tube. It's called photomultiplier. So what it does is that, as you can see here, you have visible light coming in, and it converts it to electron. So, like you have an electron, and it have diodes here. So the diodes are of like different potential. So its function is to accelerate the photon, the electron, right? So once the electron hits the diodes, then it creates more electrons. So like you keep doing that, then you're multiplying your signal. So that's the PMT over there. And I forgot to mention that the gamma camera is a monolithic crystal. So it's one giant piece of crystal. And behind it is the array of photo multiplier. So this is what it looks like from behind, and in front of it is a giant gamma scintillator actually. So how do we place the signal? So the answer is that using Anger logic. So this is a guy's name. So what you do is that let's say like your your gamma ray comes from here, right? And it creates some signal that gets detected by the PMT, and you just look at the centroid basically from that signal, and it gives you the locations of approximate locations of like where the signal is coming from. And there's a couple corrections here. One is that this is a linearity. So linearity is over there. You may not be able to see that, but the line here is kind of like curvy. And then uniformity, you can see the PMT tube over here, right? So like you see that's a PMT, that's a PMT. The reason it's being is that you can detect the signal in the PMT, right? But there's like a space in between that you cannot detect any signal there. So those are this black mark over there, and both can be corrected by maps. So some performance characteristic of gamma camera. So one is that the crystal thickness. So crystal thickness, the thicker the crystal is, so the more photons you can detect. So it improves your sensitivity. But what happened is that you pay it with the resolution. So in imaging, whether it's X-ray or like in nuclear medicine, sensitivity is always a trade-off with the resolutions, right? And the mechanism is that when you have a thicker crystals, and just to remind you, photons and attenuation is exponential mu t, right? So mu comes from your photons energy and material selection. There's nothing you can do about it once you have like the study, right? But T, this is the crystal thickness, right? So you improve the T, then you improve the sensitivity, how many photons you're detecting. However, when the scintillator detect the gamma ray, it creates a photons, right? Like a visible photons. And the thicker your crystal is, then your photons start like dispersing. So there's a blurring mechanisms over there. So crystal thickness, you make it thicker, resolutions go down, sensitivity go up. So the other thing is that distance from collimator. So we discussed that the functions of collimator in nuclear medicine is to create the image, actually is to place like the location. So that's the resolutions, right? So the further away you are from the collimator, then the resolution will go down. So the mechanism is that like if you think about it, you have this collimator, right? Let's say like I place my activity over there, then I'll probably detect the signal just over there, right? So this might be what you're looking at. However, as I move further away, then I'm start allowing these slanted photons coming in, right? You still accept that. It's because it it's defined by the collimator. So now what you're looking at is that profile. This is not to scale. So again, so the Gaussian function here represent that guy when it's close, and then the further away you move, then it represent those guy, right? So your Gaussian functions getting wider. However, the area under the curve stays the same, and that's why your sensitivity actually doesn't change. We discussed about the collimator design earlier. So there's like a couple different collimator design. Like you have higher resolution. So high resolution means you reject more photons. So you're allowing less photons. So the sensitivity go down, and the mechanism is that you make this space like longer, right? So you kind of create like a smaller acceptance angle, if you will. So resolutions go down, sensitivity goes up if you make this thing wider. So you have high sensitivity, general purpose, and high resolution. And this is what a SPECT CT scanner look like. These are the two gamma camera. So for planar, they are static. So they're acquiring the image and it's just static. For SPECT, these things will rotate. So it acquires more projections for the patients. And a lot of time, like behind this, inside the gantry, is your CT scanner. So, but to these dates, there's still like a standalone spec. So SPEC stands for single photon emission computed tomography. The computed tomography just tells you that there's a 3D imaging. And then single photon is because, like our signal is 1 gamma, right? So, that's why it's called like a single photon. And emissions, like, it tells you that the source is actually from like inside the patients. So for fuse spec CT, the city serves two purposes. So the first purpose is that to place the activity map in their anatomical location. So if you just look at image A here, okay, I get an activity map, right? But then can you tell me like, where this is located, or like even like what kind of images? You cannot, since, like you just see like the activity map, right? But once you get the city, you fuse them together, then, okay, so this activity is actually in the liver, and like, and the activity over here, the hotspot, is actually in the GI tract. So you can place where the activity in their anatomical location, or you can also rule out like, so in this case, what you see here is that, okay, so I have what looks like a liver, and hey, this might be an extrahepatic activity, right? But when you fuse it with the CT, okay, there's still part, this is still part of the liver, right? So you do not have extrahepatic distribution. So that's the function of fuse spec CT. So now the second purpose is for attenuations correction, CT attenuation correction. So like let's just discuss like what attenuations actually does to your images. So as a reminder, attenuations given by the exponential, this your linear attenuation coefficient, and T is the thickness, and I naught is the original unattenuated intensity. And so like the ratio is given here, right? So mu is a function of two things. One is that it's a function of energy, photon energy, and two is that it's a function of material, right? So like its material have different mu. For example, we discussed earlier, like bone attenuates more than soft tissue. So this is your crystal material choice, and the energy is your gamma or radionuclide choice, right? Like for example, in this case, on the left one, you see different radionuclides, and they all have different energy: technecium, thallium, and iodine. And as you can see here, no attenuation is given by this curve, right? So like it's a rectangular function, and as it gets attenuated, the center drops, right? And just from here, like this is thallium, the lower one, and the higher one here is iodine. So you can tell that just from this curve that iodine has a higher energy than thallium, right? Because like the lower the energy, then it gets attenuated more. And on the right hand side here is the effect of the T actually. So exponential minus mu T. T is the thickness. So the thicker your phantom is, then like you get like attenuated more, right? And so so that's the effect of attenuations. So how do you correct that? We discussed earlier. Your X-ray imaging is actually like give you like the attenuation map, like sort of, right? So the what you need to do is that like you have the CT images, right? And the CT images is imaged under like your CT spectrum, like it probably looks something like that. With like some characteristic X-ray, and this is a polyenergetic mu map, right? So you need to convert it to the discrete energy. So let's just say your city, you're done at like 120 keV, kV. Sorry, this is polyenergetic, right? And you just have to do some like conversion or like extrapolations, if you will, to I don't know. Let's just say like this is 140 keV, right? So that's that. Like you use the attenuation map to correct for your images. So what happened if I only have spec? It's not a hybrid scanner. So like a standalone spec. So again, like this is your attenuation equation. T, you can figure it out, right? Like okay, it's located here. That's your T. It's located here. That's your T, right? T, you can figure it out. So like what about the mu? Well, your only option is assume a fixed mu, right? So, the figure here, unattenuated profile, and then overcorrected, you assume like higher mu. So, you can see like, it's supposed to be something like that, and then it shoot up, right? And then this is like properly corrected, or you can have like a undercorrected that looks like that too. But you have to assume a fixed mu. It doesn't work that well because your anatomy is not uniform, right? So it might work in some instances, let's say like a brain scan, whereby okay, you have a skull, but the brain is somewhat like uniform or something like that. Or like if you do only the abdomen, okay, there's like a spine, there's like vertebra over there, but in the most part is uniform. Then this method can work. But given a choice, then you should always do the CT. Scatter correction, this is a more advanced topic. So, earlier we discussed that, this is where we image our the primary, right? So if you image the primary, and this is a phantom image, this is what it looks like. And then down scatter, right? Down like, at the lower energy, you have the scatter image here. So, if I acquire another image set, over there. So this is what the image look like. And the spectrum here, this is from simulation. So you have like unscattered event, the photo pic, and then you have the scatter event, right? So the entire premise is that, hey, why don't I scale the scatter here? I multiply it by some fraction, and then it should approximate like what the scatter over there, because the energy is pretty close, right? So that's the entire thing. So that's how you correct for scattering spec. Or you can also do like a physics modeling, but this is the more like kind of like a popular one, at least like for the time being. Okay, now let's switch gear to PET. So PET, it's a positron emitter. So this is the chemical reaction. So this is E plus or beta plus. That's the antiparticle of electron. So and if you're trying to figure out like what's the chemical reactions, the easiest way is that to just look at the conservation of charge, right? So if you're emitting a beta plus, then you have to start from proton, right? Otherwise, your left hand side and right hand side doesn't conserve the charge. So in this case, too many protons, not enough neutron, you convert a proton to a neutron, right? And then like you have like the positron. So positron is an antiparticle of electron. For the most part, it behaves like electron. Mass is the same, energy is the same. And once it get ejected, right? It follows this kind of like a tortuous path. You can think about it, if you have like a bowling pin, right? And instead of throwing it with bowling ball, I throw it with, let's say, like a ping pong ball. So it just like ping pong, like gets scattered in matter, right? So that's why the path of electron is always like disconvoluted. Here's the difference. Once the positron spend almost all of its energy, it will recombine with the electron, because the antiparticle shouldn't is not stable, right? In our world, in parallel world, probably they don't have electron; they're like positron based. But in our world, then it's not stable, so they recombine with electron and create what's called positronium. And positronium is unstable, and it has to go to like a more stable state. So it creates two annihilation photons actually. So and the two photons here, they are about like 180 to each other, but it's not quite. Remember when I said like right before it spent all its energy, it combined with the electron, right? So like the positron is still moving when the annihilations occur. So like you have to conserve the forward momentum, and the momentum in the orthogonal direction is taken care by the opposite directions of the annihilations, right? And what about the energy? Both positron and electron have energy or mass of 111 keV. So when it creates the annihilation photons, then both of these photons have 511 keV, both of them. So you have like there's two of them for like the conservation of energy. So let's discuss the image formations really quick. So earlier, right, like we the left hand side here, this is a planar or spec, if you will. So we cannot include this signal that comes at an oblique angle. The reason being is that your line of response has to be above it, right? Like you cannot make any other assumption, and in order to make that assumption valid, you use a collimator. However, in positron emission tomography, right? So when you detect an event at an oblique angle, guess what? You have the other annihilation photon that comes at the opposite directions, right? Now you have two events, and then you can draw a line of response over there, right? So now you do not have to make an assumption that when you detect something, it's orthogonal, the origin is orthogonal to detector. So this is like the beauty of PET. So like now your line of response is, hey, I detect it here, I detect it there, my line of response is oblique. So like no more assumption that like it's at the orthogonal. So the beauty of it, or like the benefit, is that one, sensitivity goes up. So remember that your collimator discard photons, right? So if you detect more photons, then your sensitivity goes up. And uniformity, if you think about it, like you have the septal, right, for collimator. So your uniformity will suffer because of that. And the other thing is that the spatial resolution will go up, and your spatial resolution in spec or in planar is governed by the collimator. And in PET, you do not need the collimator, so the spatial resolution now is limited to your voxel size, or or rather like detector size. So that's the beauty of PET. So now let's discuss about the coincidence detection. So what do I mean by coincidence? So okay, so we have a signal, right? Like annihilation started over there, and then you detect one signal, and you detect another signal. So what we do is that we use what we call coincidence logic. So like input B, like the event is closer to B, right? So you detect the signal first in B, and then you detect the signal in A, right? So you're looking at the coincidence window. Let's just say like, your coincidence window is about, it's about that size. So if the coincidence happens, or like, outside the window, what you'll see is that this is your detect, or like, see signal A, signal B, or like the other way around, doesn't matter. And your output is zero, because like as you have a threshold over there, right? Meaning that these two they do not overlap with each other. So like when you set the threshold, then it doesn't register it as a signal. However, if they happens to be inside your coincidence window, so you have like input A, input B, and then when you sum them up, now you have this guy, right? And you put the threshold just below it, so now you get an output. And this is called like a coincidence logic. So when they happen, like similar, like close in time, and you get the coincidence. And when they happen, like relatively far apart in time, then you do not get coincidence. So what type of events, or what type of coincidence do we have? One is that true coincidence. What it is that hey, event happened here, or like annihilation happened here. You detect one event, two event, beautiful. You get your line of response over there. Like it's a correct one. That's what you want. And then you can get a scatter coincidence. Events here, one, you detect a proper signal. The other photons, or the other annihilation photons, get scattered, right? So like you detect it somewhere else. Now your line of response is over there. So the spatial information is corrupted already. And for scatter coincidence to happen, you do not need both photons to be scattered. As long as one is scattered, then like your spatial information is like corrupted already. And the third kind of coincidence is random coincidence. So you have two unrelated events, right? Like decay one and another decay over there, and one, you detect one photons over there, the other ones like you do not detect, and it happens with this guy as well. Like, this one is not detected, or it could be absorbed by the patients, whatnot, and you only detect the singles. And when you detect the two singles, then it creates a random. And, well, you get the line of response, right? But, the spatial information is not there. And now I want to introduce you to a concept called time of flight. So, let's assume that, we have like two opposing detector, right? And this is where the event's coming from. Then, you detect like, event two, event one, and you know that you will detect event two, right? Because it's closer, and you detect event one, like, sometime later. So now you have like a system of two equations, right? It's because first of all, like, when you detect it, you know the time difference, right? So now the only thing that you don't know is like either T1 or T2, like, either time one or time two you pick. And what about the distance? I know the relationship between D1 and D2, right? Because, like once I detect it here and detect it there, I can draw my line of response, right? And I know how long it is. So now we have like equations of like, a system of like two equations with two unknown. And if you solve this, then you know where the event originates from, right? And this is a concept called time of flight. But of course, this is in ideal case situations, right? Because your detector have a finite temporal resolution as well. So, like it's not like, you detect it instantaneously. So, it doesn't happen. So what happened is that, with the time of flight capable scanner, so you drop your line of response. Initially, you get a line of response. It can be anywhere between these two events, right? But with the time of flight technology, then your line of response getting shorter. It's not like it's not a pinpoint like that. If it happens, then like it means that you have like an infinite time resolution. So that's not the case. So the time of flight actually it improves your contrast. It does not improve your resolution. I repeat, like time of flight improve your image contrast. It does not improve your resolution. So in this case here, you have the city images, right? You have like non-time of flight and time of flight. You cannot see the lesions over here. So you cannot see anything there because it's low contrast, right? And you can see it over there. And the reason being is that with time of flight, when you reconstruct the image, it converges faster. So you can think about it as, hey, I mean, you have a partner, and then your partner forgets, like, his or her glasses, right? And call you and ask you, hey, can you look for my glasses? It takes you forever to look at like the entire house, right? But if she told me that, hey, it's on my counter in the kitchens or in the bathroom, then like I can go there, and well, in my case, I still will not be able to locate it, but you get the point. Like the point is that it will go much faster. So again, like the bottom one here is the phantom images. Oops, sorry. So this is a phantom images, right? So it's the same, like non-time of flight, and here is kind of like the timing resolution, right? As the timing resolution increase, then like you start improving your contrast. This is what your PET-CT scanner looks like, positron emissions tomography. And I think like all PET are a hybrid scanner. You have both PET and CT. So I haven't seen like a standalone PET at all. And the difference between the gamma camera, like a couple of things. So in terms of the form factor, PET detector is a ring. It's because you want to detect like the annihilation photon that comes at two different directions, right? So like it comes in a ring. So like it's not like two head. And the septal here, like well, I mean this is not a collimator, by the way. Like it's a septal for like axial directions, but we no longer use it for all intended purpose. Like let's forget that it's there. The table here that you're looking at is a scintillator detector property. So like your gamma camera is a monolithic crystal, and this is your PET detector. Your PET detector is still a scintillator, but it comes in a smaller block. So like this is your PMT. So like it So those this unit that I showed earlier, it's like it's each of this. So it's more kind of like a regional instead of like a big monolithic crystal. So a couple things that I want to point out. This is for spec. Like most of the spec scanner use sodium iodide or like sometimes like cesium iodide as well. This is your spec, right? And these three are your PET. So first of all, the difference is that if you look at the density or like the atomic number, this three is much higher than these two, right? The reason being is that for PET, you're imaging at 511, so your energy is higher. So you need to be able to detect the photon. So you need something more attenuating. And the other thing that I want to highlight is the photon yield. SPEC have a higher photon yield than PET detector. It means that the energy resolution is better in SPEC than in PET. And the last thing is the decay time. So this is related to your time of flight capability. So for it to be able to do like a time of flight, you need like a lower decay time. So you can think about it as decay time is like kind of like an afterglow, So when I detect my photons, like my annihilation photons, like in ideal world, it creates all the visible light right away instantaneously, but it's not the case. So what happened is that it detects it interacts with the annihilation photons and it creates the visible light over time. So the longer, if you imagine that if it get hit and it glows forever, then you do not have a temporal resolution, right? Because you don't know when the event happens, So that's the decay time. So this is pertaining to time of flight capability. Um, PET resolutions. This is a curve from distance from the center for both SPEC and PET. The spatial resolution is the best at the center. However, SPEC degrades like faster as it goes away from the center. The reason being is that it's governed by the collimator, right? As you move from the center away from the center, then you start increasing the distance from your collimator. So in PET, it doesn't happen as quickly because you do not have a collimator. But the degradations mechanism is that if this is the center, right, and you're looking at the bore of the PET, and if an event happens on the site, let's say it happens here, what it does is that the effective detector size increases, right? So if it's at the orthogonal, then this is your detector size, right? However, when you come at an angle, then your detector size, like the apparent detector size, is bigger. It's because the detector doesn't know whether the event happens here or the events happen there, right? Since this is a single unit. So this is called a depth of interactions, and that's one of the blurring mechanism in PET. And the other blurring mechanism is the positron range. So I mentioned earlier that when the positrons get emitted, it has an energy, right? So it travels in some distance. So the further away the positron travels, it means that the resolution blurs, right? Because you have the point of decay, right? Let's say this is my F18, right? And then your positron actually create a positronium over there. So this is the blurring, right? So the higher the beta plus energy, the worse your resolution is. So in this case, there's two examples. So oxygen 15, 1.7 MeV, F18 is 0.6 MeV, and you can see the spread. So F18 have a less spread, and if you draw the line profile, the full width half max is 0.1 versus 0.5. So this is another blurring mechanism for PET. Okay. Tomographic reconstructions. How do we reconstruct our projections, right? One approach is called back projections. And in this case, what I'm showing you is a simple projection. So let's say this is view one and this is view one, right? And if you think about your detector let's just say your detector over here, right? So what you're looking at is a profile that looks like that, right? Like, I don't see anything. I see something over there, and I don't see anything. So that's what it looks like. You keep doing that, like, as you add more projections, right? So, one projections, two projections, and just keep adding it, and eventually you'll create the 3D image. And this is a simple back projections. And we don't use it that much in nuclear medicine. So the more kind of like accepted method is iterative reconstructions. So let's say like you start with an object, right? And you acquire the projection, and this is your acquired projections, okay? And then I start with some image estimate. You can estimate it as a blank, doesn't matter. And then okay, if I have, let's say, like some estimate of the object or blank object, I can create the projections, right? I can calculate the projections. So I calculate the projections. Okay, if the image looks like this, then the projections will looks like that. Okay, and there's the calculated projection. You compare it with the acquired or measured projections. So how do these two compare? So are they similar? If it's not, then like you update your estimate. Okay, and you keep going on and on till it converts. So like that is like an iterative reconstructions. Once it converts, then are they converging, or do they look similar? Yes. Then you terminate it. So that it's a nutshell. Like it's more complicated than it actually is. So this is an example of like the iterations, right? Like this is a brain scan. You start with just like some blob, and then as you iterate, then you start adding more and more detail until it finally converges. Okay, so that's all I have. In summary, like we spent an hour talking about the imaging, emission imaging. So one thing to take out is that like emission imaging is functional imaging. So that is different from anatomical imaging in X-ray or in MR. And then we have compare and contrast like transmission and emission imaging. Hopefully, like at the very least, like how planar, spec, and PET imagings are formed. And again, like, we discussed about the image formations in nuclear medicine and PET. All right, that's all I have. Thank you. And we're right on the time.